side, we're going to see Aaron throw the ball to Carl from first base to home plate, which is 90 feet. It takes the ball 1.21 seconds to get that distance. We're going to find the speed because speed is in the second chapter of physics. To find the speed, we're going to take the distance and divide it by the time.
Pick up a pizza, pineapple, ham, and put it in the back of a Good Times van. Go out and pick up the rest of the band. We're gonna have a good time. Yeah, Lily of the Valley, Lily on the rug. Lily drove here in a VW bug. Am I on the guest list? Give her a shrug. We're gonna have a good time.
Is 74.38 feet per second. This is the speed that the baseball travels. The second plug-in check today, we're going to find the gravitational force between the Earth and the ball. So the mass of the baseball for M1 is 0.145 kilograms. The Earth's mass is 6 times 10 to the 24th. The gravitational constant is 6.7 times 10 to the negative 11th. And the distance up the ball is, at the peak of Aaron's hit, was 15 meters. So we're going to take that and plug and chug it into the equation you should know and come out with the gravitational force. The equation you should have plugged it into is the constant g times the first mass times the second mass divided by the distance squared. So you're going to take 6.67 to the negative 11 times by the result of 0.145 times 6 times 10 to the 24th divided by 15 squared. These two multiply to equal 8.7 times 10 to the 23rd divided by 225 equals 3.86 times 10 to the 21st. So we're going to take 6.67 times 10 to the 11th and times it by 3.86 times 10 to the 21st. And we get 2.57 times 10 to the 11th g. And that is how much force the Earth is pulling on the ball, and the ball is pulling on the Earth because they're equal.
We love physics.
This is an arc with which the ball goes after it's hit by a batter. The batter's standing here and it's caught over here. At the bottom, it has all potential energy and no kinetic energy. And when we reach the tip of the arc, it has all kinetic energy with no potential energy, reaching all potential energy again at the bottom. And anywhere in the arc, it has the same total energy, and total energy is the sum of potential and kinetic energy.
Is a baseball. I'm going to teach you how to throw a curveball. So what you do is you put your fingers like this around the seam horseshoe right here. You're going to hold it like this. And when you throw it, you're going to snap. So it gives this rotation right here. And what makes the ball curve or drop is the amount of high pressure of the air resistance right here and the low pressure right here, creating the ball to go down. And the seams and the way the ball is spinning gives it a little curve. That's why when a batter's looking at it, it's breaking away and down from you. This is how a knuckleball works. So when you throw a knuckleball, you have your fingertips in right before the seam, if this was a baseball. And as soon as you let go, your fingers are going to snap, creating no spin on the ball. Now, after you let go, it really depends on where the most resistance of the air is at the time to tell where the... So, say the air resistance was all straight on. It would move like this and then potentially drop. So the way that the air hits it, it could make it move anyway. So like say because wind comes and it moves this way, drops down here. Say it's a warm day, it's gonna have more pressure on top and it's gonna drop down. That's why a lot of knuckleball pitchers have a hard time directing it in the strike zone because no one knows what's going on. Next slide, you're gonna see work done from soft toss. Now, he's gonna pitch it up to me so the ball has very little force coming at me, and I'm gonna exert my force with my bat speed to create the distance. But if you have a pitch which increases the force with this constant bat speed, so bat speed doesn't come into this, if the force gets bigger by the pitch being faster, then the distance is Next clip, we're going to demonstrate how when you cushion a bat, how it absorbs most of the energy and force, and if you don't, how it bounces off very firmly. So if you don't give the bat at all, or cushion it, it's an elastic collision, and it bounces far. When an inelastic collision, you give, and it slows the time for the ball to stop, and it sticks. And then it just falls. So when you're bunting, you give it a little, and it stops.
Next slide you're going to see is about center of gravity and what happens if you are not over your center of gravity at all, but you don't topple because you're still slightly over it. Or when you are and your weight is able to transfer, you can hit the baseball to the moon. But you have to hit it 3/4 of the way there because the moon's small and has less gravitational pull. We're going to demonstrate what happens when you hit a baseball with a softball bat. Softball bats are lighter and made out of the same thing as baseball bats, but since there's less metal on it, they can't withstand the pressure from the little baseball instead of the larger surface area. This is a bat after being hit by a baseball. Notice the dents in it, which are pretty huge.
They said they wanted speed. They said they wanted power. They said they wanted Beyonce on a ham sandwich. Well, 2.5 out of 3 ain't too dang shabby. Jukebox Plus. Rip faster. Burn better. Super tag. It's just way better. On a ham sandwich. Get Plus now.